Now is it, yeah, is it visible now?
Yes, yes, it's visible now. Yes, yeah.
Yeah, okay. So the topic for today's discussion is model-based design and development for advanced driver assistance system. So before going into the topic, I just request the people to place the call on mute. In case if there are any questions, you can just note them aside, and then we can have a Q&A session at end of the discussion. So apart from that, in case if there are any sort of power fluctuation or anything, just please bear with me. I may have to disconnect and reconnect. It's basically the connectivity issues, maybe from my side. Okay. So the topics that we are going to see for today's discussion is about the overview of automotive industry, software development demands in automotive industry, and where does model-based development fit into the automotive industry. So about that we will see. So the first three are more generic topics. So in detail, so inside model-based development, we have different layers. So they are like requirement analysis, and then we switch over to the Matlab tool. So inside Matlab tool, there is something called as configuration parameter settings of control models. And then about the data management, Simulink data dictionary. So this will be followed by signal names and signal property configuration and other things. So final stage of model-based development is model simulation, model advisor report correction, and then that would be followed by code generation settings and auto code generation. So the third part of our discussion would be around the testing theory. So this will be followed by the test report analysis and overview of MIL, SIL, and HIL, that is model in loop, software in loop, and hardware in loop related testing. So the final part that we will be seeing is about the introduction to advanced driver assistance system and different levels of advanced driver assistance system or autonomous driving, and where exactly or how exactly we can try to fit in ADAS feature into this. ADAS feature into the MBD environment is what we are going to see. Okay, so now let's quickly move to the presentation topics. So to start off with, so this is an overview of the automotive industry and who does what in the automotive industry. So if you can see from this picture, it is quite clearly understandable that there are three major players as far as the automotive industry is concerned. So one is the OEM, that would be followed by the suppliers, and the third stage of it is like the people who provide support to both the OEMs and the suppliers. So the OEMs here are the original equipment manufacturers or the ones who make cars. Okay, so they basically have a problem, they have a design, and they try to provide, or they want solutions basically to most of their problems. So their problems are of different levels. They can be design related problems and manufacturing related problems, or sometimes electrical and electronic and computation related problems. So they have problems and they want solutions at different levels. They need a mechanical design, they might need a manufacturing component, they might have to go and manufacture a component, they might seek the help of say a different supplier to supply them some specific components, and all that is there. So a car is simply not just the body, the chassis, or the doors, the windows, the seat, and the steering column, the transmission, the powertrain, and all. Okay, so a car as a whole like has hundreds and hundreds of electrical and electronic components that is associated with it. Okay, so if we have to look at the history of automobiles and the four-wheeler markets overall, like in the 1980s and the mid 1980s, if you can see, globally, I am saying that cars started using a lot of electrical and electronic components. Like they were not only completely mechanical reliant, a lot of electrical and electronic components started coming into cars. Okay, to put it in a very, to quote it with an example, if I have to say, like in the 1990s, if you can see, in India, in cars, say something like our very own Maruti 800 and other cars and all, they started using these electronic wipers, and they started having some sort of music system which is like detachable and attachable into the cars. So those kind of electrical and electronic components were there. And apart from that, some basic level sensors were also there, basically to calculate the engine temperature, the fuel level that is present in the car, the speed at which my vehicle is going, the exhaust gas related pressure, so sensors related to that. So these kind of sensors were being used. So in order to control the system performance, basically, we had to sort of say like play with these sensors, get the data from the sensors, process them, and then we have to send it back to the actuators such that they will give a desired output over here. Okay, so this is how the whole system is built. This is how exactly the control system is built with automobile systems and automobile industries over here. Now, when you look at cars in the 1990s to the present day cars, obviously the list of sensors and all, they are there, but I mean the basic sensors, whatever I had told initially, they are there, but their numbers have gone up drastically. From like having 5 to 10 sensors, today cars have close to 1,000 sensors. From having 1 or 2 ECUs, today high-end cars, you take any high-end car which is being manufactured somewhere in Europe or US, say like a Tesla or a Mercedes Benz, so these kind of vehicles and all have close to 50 to 70 ECUs, that is electronic control units alone for a specific function. Specific ECUs are there. So back in 1990s, we had one ECU which will handle n number of sensors that is present in that vehicle. Say a Maruti 800 had only one electronic control unit. Okay, but today's cars have n number of sensors. Like the number of sensors has multiplied at least 20-30 times, and also the number of ECUs has gone up drastically. Even if you take a passenger car that is like what we buy in Indian market today, a budget car, something like a Santro or a Tata Tiago, even those kind of vehicles have close to 5 to 8 electronic control units that is associated with them. So the more costlier car that we try to go, the more number of sensors that we have to play with, and obviously the more number of actuators that we use, more ECUs we use, and basically a lot more computational complexity is associated with it. Okay, so when OEMs are looking at these kind of problems, that is from electrical and electronic standpoint, and when they are seeking solutions, they cannot seek for solution. They do not have all the solutions within themselves. They have to seek the solutions. Basically, they have problems which can be split up into n different levels, and they are trying to seek the solutions. So where do they go and seek the solutions in first place? So the first set of people to whom that they look for solutions are the electronic control unit suppliers. So these electronic control unit suppliers that we have in today's market are people like the Bosch, Delphi, Continental, Magneti Marelli, Hella, etc. So OEMs like Renault or Ford or Volkswagen, so these guys they manufacture their vehicles. They want their software to be packaged in such a way that it is quick enough to process the defined control algorithms and provide them a solution. So since you are having more than hundreds of sensors and the corresponding actuators that is associated with it, and the control algorithms are like very, very, what I would have to say, like they're very complex and other things, you need to develop foolproof algorithms for the market, and the OEMs cannot do it all alone in first place. So it's a combination of work that they adopt, and the first set of people to whom they seek the support is people like Robert Bosch and Delphi and Continental. So these guys in turn will seek the support of other second level people. Okay, the tier 1 ECU suppliers are people like Bosch and Delphi over here. So beneath them, we have some other people who are going to support both my OEMs and my tier 1 suppliers in providing solutions. So what kind of solutions that they are going to provide. Say I have to do, say I have to develop my software. Say I have to validate my software. Okay, so there are different stages of validation. So there are different levels of support that is needed. So there are some certain tools that are there in the market, which is going to help me to validate my final control software that is going to be manufactured. So this is where these people, that is the tier 2 suppliers, are coming into the picture over here for subcontracting kind of jobs. So people like National Instruments, or say like Matlab, MathWorks. So these guys, these kind of guys, they come in, they understand what is the need and the problems that the OEMs and tier 1 suppliers are facing with respect to the giving the final production software and the other things. So they analyze them, and based on that they build tools, and they try to provide solutions to them. So it's the support is always like complete, like from the top to the bottom, and from the bottom to the top is what the electrical and electronics part of the automotive industry basically is. So this is a very detailed workflow of like what happens in the automotive industry over here. And to put things into a perspective, like these are some of the different systems that is present in automotive system, a modern automotive system. Today, briefly classified under like ADAS, for advanced driver assistance system. So like if you can see here, they are in red color, something like emergency braking, blind spot detection, front camera view system. So the powertrain and chassis are related to the vehicular movement and the other things, where systems like my internal combustion engine, the fuel pressure, and other associated systems that is there with it. And then that is followed by body control modules. Body control modules like stands for whether my airbags are working fine, whether my windows is like power windows are working perfectly fine, whether my battery is there, perfect battery is like working perfectly for the system, and the other things. So that is followed by infotainment
Alex,
systems.
sorry to
So
interrupt. Your audio is very noisy. Uh,
uh,
we're not able to
okay,
hear your voice.
oh, okay, ma'am. Like 1 second. Can you just
Yes.
give me a minute?
Okay, sir, sure.
Yeah, yeah. Hello, ma'am. Is it audible now?
Yes, sir. Yes. Now it is clear.
Yeah. Okay. Sorry.
Okay.
So I think there is some problem. There was some problem with my
Oh,
earphones. That's the
okay,
problem.
sir. Okay. Thank you so
Yeah.
much.
Okay. Yeah. I can. Can you just be online for a minute, ma'am?
Yes,
Just
yes,
one
yes.
minute.
I am online now.
Yeah. Yeah. Sure. Is my screen visible now?
Yes, sir. It is visible, sir. The audio is also clear.
Yeah. Okay, ma'am. Thank you.
Okay. Thank you, sir.
Okay. So coming back to the topic.
Can you make it
So this
slightly?
is about the. Yes, ma'am.
Okay, sir. No, no. Continue, continue. Thank you.
Yeah. Thank you. So this is about the different systems that we have basically. So when we are talking about this thing like control models and other things, it is for these systems that we try to develop control algorithms. So if you can see some of these systems that is present over here, something like a heads-up display, or something like a battery management system or a HVAC control module and all, So these systems have some few sensors and some actuators associated with it. So the sensors brings in the signal, which will be processed in the ECU by these systems, by the specific control algorithms, and it will be given out. So how the workflow here is basically split up and given. The problem is standing with the OEM. The OEM has the algorithm. Okay, so this algorithm, which will be in the form of a diagram or a flow chart, has to be converted and flashed or put up into the ECU. So what is going into the ECU is a machine language, right? So this is, this is a machine language which is understandable in the form of zeros and ones. It is not even a C code. Okay, so when it is like a stage after the C code basically. So when you are looking at those algorithms and all, like basically the computation level that these algorithms go and all, here only the OEMs started facing problems like 10 or 15 years before. Okay, so what exactly were the problems? As far as like most of us know, when I finished my college degree and all, when I finished my undergraduation and all knowledge that I had was like C code means it is like only handwritten codes. Okay, so when C codes were completely handwritten, it takes a lot of time to understand and write. The competency level that an electrical engineer or a mechanical engineer has in comprehending a C code is different from what an IT engineer does. So the problems for the OEMs where they were exactly is like they wanted a mechanical engineer who is very good at understanding and analyzing about the system. When you're talking about a powertrain control system means when you have to deal with something like boost pressure and other related components, when you have to draw maps for those system means you are going to talk about pure mechanics and physics behind it. So you need a mechanical engineer for it. Then you also need an electrical engineer when you are talking about different signals, the units that they are going to handle, when they are going to be flashed into the ECU, how they are going to respond, and the other things. And finally, an engineer with like computer science knowledge or coding knowledge. So basically, whatever information that my mechanical engineer and electrical engineer are going to give, that part of work my software engineer is going to write in terms of code. So it had a lot of disadvantages basically. So this was the practice that was there like 15 years or 18 years back. Okay, so this actually had a lot of disadvantages in the industry. So what sort of disadvantages? Like it dragged the work, and the algorithms were not foolproof. Okay, so they developed the algorithms, but they were not completely foolproof. There were more chances of errors coming in those algorithms. So the biggest challenges the automotive industry faced in terms of the software development demand were the quality and the cost, debugging million lines of code, efficient calibration, and selecting across variant. Okay, so the selecting across variants here means like you will have the bunch of software that is developed. From that given bunch, you will try to take your software from one variant to another variant. Maybe like you will have hundreds of millions of lines of code for different applications developed. But for lower division vehicle, not all would be used. But for a higher division vehicle, all the lines of code will be used. So when you're trying to port that software from a higher division vehicle, from a high variant vehicle to a low variant vehicle, you have to comment those lines of code in such a way that it does not affect the other systems that is associated with it. Okay, so these kind of challenges and all were there. So one of the biggest solutions when they put these points for the forth to OEMs or like tier one suppliers about these problems is, so like one of the biggest solutions that the tier one suppliers came and gave the OEMs was something like a model based development. Okay, so what exactly a model based development could do here? Okay, so they actually had a lot of solutions coming up with a different standard architecture and parallel software development and multi-core ECUs and all that was there. But one of the key things that the companies came together with was about this model-based development. So why essentially this model-based development is? See, automotive industry is something like that is results driven, like any other OEM and organization, because companies would be working on a parallel technology sometimes at the same time. So who takes it quicker to the market, they will be able to sell their product better to the customers. So in the quest of taking your software much quicker to the market, people spend enough time to test and validate it. They might have spent a lot of time in developing the algorithm to design it and all that, but they may not spend enough time to validate it at different levels and then to push it to the market. So this data, whatever that we are seeing in screen, this is all about the vehicle recall, which is basically because of faulty softwares. The software that an engineer sits and writes, it has a lot of problems, and that is where the whole thing here is like happening. So the whole funda here is like, if the software is breaking, if there is a faulty software that is found, that vehicle has to be recalled. Vehicles similar to that will also have similar problem, because your software, whatever that you're developing, you're only going to develop it once. Because after developing that software once, when you are trying to take it to your that single software will be flashed across multiple vehicles. That car will be manufactured to the market for 5 years only you're going to use. You're not going to keep like, for if you want a car mean type software, you're not going to manufacture. You just copy paste the same piece of code and you're going to keep pushing it. That's the only thing that's happening there. So you have to recall all the vehicles, fix it in every vehicle. Okay, because you have to take that car, that particular piece of code, again you have to reflash it, which is going to take a lot of time, and the reputation of OEM here goes for loss. Also, different engineers, or at least two different engineers, to do the same job. Okay, so with the advent of something like a model-based development, the job shrunk massively, because you are no longer sitting and writing a C code, because you have a tool which is going to generate and give you the code. All right, that's the whole thing behind model-based development, and the expertise of, and it also made the job a lot easier for core engineers, someone with a quality electrical background with good knowledge on mechanical systems. He can go and work in software development part. He can contribute himself to it. So that level of leverage started coming in with the advent of model-based design. Okay, so what exactly this model-based development and model-based design means? So again, has three pillars, I would say. So they are modeling, simulation, and it's basically algorithm development. Your OEM a problem.
Sir, sorry to
This
interrupt
problem they
again.
come with
Sir, audio is breaking. Balaji, sir. Yeah. The audio is not clear, sir.
okay,
It
like
is
1
breaking.
minute, ma'am.
Yeah.
Better now, or like
No, sir. No, no. It is breaking.
again 1 minute,
Okay,
1 minute.
okay.
Just quickly stop sharing it and I'll rectify it, ma'am. 1 minute.
Okay, okay.
Hello, ma'am,
Yes,
is it
sir, it is
audible
very
now?
clear now.
Yeah, okay. Thank you.
Okay, sir.
So I'll quickly share my screen
Okay,
again.
sir.
1 minute. Sorry, like for this,
Sir,
like
no
there is a
problem.
power cut at my place today, and
Okay, sir, no problem.
so the internet is not there basically.
No problem.
So I hope the screen is visible.
Yes, sir, it's perfect.
Yeah. So coming back to this, so this is so the model-based development has three major verticals or pillars that is associated here. So one is modeling, the next one is simulation, the third one is validation. So what is modeling here? Modeling means like basically you have an algorithm, you are going to convert that algorithm into a simulation model. So here, say for example, there is an OEM like Audi or Mercedes Benz. They have a problem that is readily available with them. So this problem, whatever that they have that is available with them, they will try to go to an OEM or a tier one supplier, because tier one supplier like Robert Bosch or Continental, so these guys manufacture ECUs. So rather than simply selling them the ECUs, they come up with a plan like, we will also develop and give you the control algorithms. So along with the ECU. So while developing and giving the control algorithm, we will also validate them and test them at different levels in our laboratories and in our systems, so that you can take that, you can put it onto your vehicle, you can do the final level testing, and then you can release into the market. That's how the whole deal is made between OEMs and tier one suppliers. Now, in this case, when they want to develop some models which will be converted as a C code, basically, they seek the support of these tier one suppliers like Bosch, who in turn look at using which tool we can develop models that will be converted into the C code. So the most widely used tool in automotive domain, which the companies, which the OEMs use for converting the model into a C code, is Matlab Simulink. Okay, so this whole part is modeling, where you convert your problem into where you convert your algorithm into a simulate model. So this stage is modeling. So once you have done all the modeling part, it is not like simply we just understand, we just look, okay, I have signal 1, signal 2 coming, I need to add these two signals and give signal 3, and I can try to do a code generation. No, it's not like that. There are different standards that the companies must follow while trying to develop model. Like how you have safety standards of ISO for a physical component, for the manufacturing vehicles, even for your software that is manufactured, it needs to be put through different ISO standards, and it must adhere to all the standards. Okay, so based on that only your system needs to be developed, and there are certain guidelines of how you need to develop it, right from using a specific Simulink block from a Simulink library, how you need to have it, how you need to place it, how do you have to define values to it, which property needs to be enabled, like that, and all, a lot of things are there. So usually different OEMs have their own rules and style guidelines in developing it. But Matlab itself has come up with something called as MathWorks Automotive Advisory Board, which is MAB. Okay, so they have their own guidelines, and based on those guidelines, you have to develop model. So once all the model development part is done, the next stage would be to do a simulation. Simulation is done basically to ensure that I give some set of inputs, and then my output is coming, basically taking care of all the data type and the dimension related connectivities. Okay, I have a signal which is of uint 8. Then I may use a different signal of uint 16. Some other signal I may use will be of Boolean data type, or a single or a double data type. So when I am trying to deal with different number of signals of different data type, and when they are going to be added or multiplied, or when they are going to be given to a lookup table, the output of a lookup table can be of different data type. So all these things are going to happen. Few signals can be single dimension, few signals would be like an array.
a multi-dimensional signal. So when you're trying to handle all these things, you need to ensure that there is a consistency in data that you are sending as input and what is going to come as output. So all this is taken care of at the simulation stage. And finally would be the validation stage, where once the simulation is done based on the requirement, okay, so far the work was at the developer's end, then the work will be at the tester's end. So where usually once my whole system is ready and all that, the test, I mean the test engineer, based on the requirement document, will try to send in my datas based on the signal data type and others. He'll try to define the test vectors. Based on that, he gives for some specific set of inputs, I need exactly specific set of outputs should come. Like this, they will do it. And this kind of testing is of different levels. Okay, model in loop, software in loop, and hardware in loop. Basically, what they are and all we'll be seeing later in the presentation. So this is basically about the model-based development and different verticals of a model-based development. Now, quickly looking at this, so this is something that they call as software development life cycle. So when you go to basically organizations and all, like any companies, not only automotive company, any organization you go, they follow some specific software development norms and guidelines. Okay, so one of the norms and guidelines that they try to follow here is software development life cycle. So they follow a specific pattern. Using this only, like this is identified as one of the best ways to develop my software and try to release it into the market. So there are techniques like the waterfall model and all, but they have adopted this software development lifecycle model, where my whole problem, okay, that is my algorithm, and my model development, that is my problem statement. From there to model development, from there to code generation, and then from there to validation. This is like even further split up, identifying individuals' roles and their responsibilities. Okay, so usually the OEM comes with the software requirement analysis and they give it to a project manager. So this project manager will give to the development team. So this project manager, under him there will be two teams, a development team and a testing team. Each team will have a lead kind of a person, where this lead engineer will analyze the problem. At this stage between the program, the project manager uh, of the development team and the one who is giving him the problem, the guys from the OEM, they'll have a lot of interactions based on which the design will be freezed. So once the design is freezed, they will try to again split the huge design into different levels. Okay, because if you're taking say for example you're taking a Matlab Simulink model, which is going to have at least 40 to 50 subsystems of different level. If you're taking like that, means the generated code will be like nearly 5,000 to 6,000 lines of code, and to develop such a big algorithm would take a lot of time. So what they will do is, again, by using this model variant subsystem and other concepts which is there in Matlab Simulink, they will try to split it completely. So once that whole 50 subsystems are split as 5 subsystems across 10 people, development will be done. There will be one integration engineer who will try to integrate everything, all the variant subsystems together. So once this all is done, they will do this model in loop testing and validation over here. So this model in loop testing and validation, in very short, if we have to say, whatever model that I have developed, I will be having some specific set of input values. When I give those values to my model, it must reflect and it must give me exactly the expected outputs. So this will be done at the model level. So this is called as model in loop testing. So usually tools like Matlab or BTC or Reactus, so these kind of tools are like predominantly used by the OEMs to do the job. Okay, so once this model is developed, then they run something called as a model advisor report, where this model advisor report is going to check for the quality of the model, whether the model that I have developed is as per the industry recommended standards, whether it is satisfying all the ISO and other things. So basically, when you're talking about the automotive software development, the ISO number that they use is ISO 26262 standard. So this is what that all the OEMs and tier 1 suppliers and companies have to adhere to while developing the control algorithm software for automotive applications. So whether my model is developed based on this, so this is a tool which will do a background check for every block, every subsystem. It will verify its properties. It will verify the C code that is generated also, and other things are there. So this model advisor report does it. So this will be followed again by the code generation, where depending on the end user which architecture he wants. AutoSAR is a very generic architecture which the OEMs follow. Apart from that, there are specific architectures what the OEM might follow. So whether he wants a generic architecture or a specific architecture to do code generation. So once this is identified, taking this into consideration, they will do the code generation. And once the final C code is ready, the C code that I am talking here is the code with .c and .h files alone. So once this part of code is ready, they will do a software in loop testing, where basically the same test vector signals will be given as input, and then they will try to check whether they will basically replace the model with the software. So both model in loop testing and the software in loop testing will happen at the computer level, and they need to do these testing here, and the software quality would be determined. So once these two stages are done, the next stage would be like going to a different team. So the development team will do the development. Sometimes the mill validation and SIL validation will be done by the testing team, and hardware test engineers are separate, sort of like third teams. If the development team itself is doing both mill code generation and SIL everything, means the second team will only do this hardware in loop testing. Otherwise, it will be a combination of three different teams here. So these guys will basically take the C code, try to convert it into something like a .hex file or an object file, and others. Basically, we'll try to convert it into a machine language. Then after converting into a machine language, they will try to flash it into a ECU, where this ECU is the final production ECU. Okay, so they will flash it into the ECU. Now this ECU will be connected to a big hardware rig, which is basically they will call it as MRET or a DSpace device. Okay, so this hardware rig, it will be connected via wires and different harnesses. So once all of this is like completely done, they will do the testing and validation at this stage to see whether the given signals and all, they are responding or behaving properly. So basically, so far in our simulation, all the sensor inputs and all we will give manually, and the actuator outputs we will be seeing at the output level using a scope block or something. Okay, so this was done at mill and SIL stage. Now you will have a prototype of sensor that is fixed. Okay, so this prototype of sensor will give me signal input that will be connected to the ECU via this hardware setup. Okay, so now my ECU will process the algorithm, which is in the form of a machine understandable language in 0 and 1. It will give the final output. That final output will go to an actuator system, which will it will be something like a breakout box or something, which will only going to flash a light and tell me. Okay, so when all of this is done, it means like even my hardware in loop testing is correct and validated. So the final stage of it after this would be to release the software. So this is the complete cycle that is involved in the whole process, basically with respect to the system. So under this, when you can see, as far as developers are concerned, what are their different roles over here? So one is to do the requirement analysis. Next one would be the model simulation. Then it is testing and validation, followed by auto code generation. So this, I think we have already briefly explained. Requirement analysis is like you sit down with the OEM, the design engineers from the OEM, the design engineer from the OEM, and from the suppliers design lead engineers. So these guys, they sit together, they try to understand each and every line of the requirement. When you're taking a specific functionality, means the requirement document itself will be like something like 70 to 80 page document. So you need to sit down, you need to understand the requirement here, and then every stage of the requirement you have to comprehend here, and then that needs to be converted as a Simulink model. So this Simulink model in turn will be code generated and then tested and validated. So in previous days, or the traditional cycle, what they basically had is like the one at the top that I have shown here, it's the traditional cycle that they adopt. So in the traditional cycle, they try to understand the problem and they try to type a C code, which they will flash it into the ECU directly, and they will test it. So in this stage of development, your model in loop and software in loop validation is neglected. So once your model in loop and software in loop validation is neglected, means we will miss out on whether we have done the correct development, because any error that is there, if we have understood the requirement wrongly, and if we have done the development or whatever, so all of this will only be identified at the final hardware in loop stage. So then we have to come back and do the corrections. Then we will again take it back to the requirement team from the OEM. They will tell, no, you have done the mistake over here. We will do the corrections, and then, so even when coming back and fixing it will take a lot of time. But when you are adopting a model based development approach, any issue that you find with the model in loop simulation, we will quickly understand that, identify that, go back to the model, quickly fix it, do all the necessary changes in the model then and there, and then try to do a model in loop simulation. See, basically there are two different models. For mill testing, you will have a model, the final Simulink model that you will have. So basically, you will take the top level subsystem and put it into that. You will have some, it will have some defined set of inputs and outputs. You run mill testing. When it throws any kind of issues in mill testing, basically when it does not give the expected result, we will identify that, okay, there is a design error that the developer has done. So he will have to go back, fix it, and quickly he can come back. So the whole time that it takes to fix an erroneous one is very less in model based development compared to a traditional system. So this gives a lot of time for the development team to sit and validate, because the moment we try to sit and validate at different verticals, means we can give expected results. So that's the whole thing over here. And what are the major benefits that the companies see with model based development? So one is about the models. The next one is a very quick evaluation of the different variants, because remember we were talking about something like, if I am going from a higher variant to a lower variant, I have to comment my lines of code, we were telling. Here it is not like that. You can simply comment out a model so that it will automatically generate the code appropriately. Once you are commenting out the model, means it will automatically generate the code appropriately. So again, the engineer need not take time to check each and every line of code in case of handling different variants of the model. And testing and validation can be done at each stage. So this will massively reduce the development cost. The reason is, when you're adopting a traditional approach, if there are cases where you are not fixing, if you are not identifying any bug even at the kill stage, it goes for production. At the production, I mean, it goes for production. The vehicle is out in the market. When the driver is facing it real time, to recall each and every one of them and to do fix it manually as is like the approach is traditional. I have to now go back, understand the algorithm, understand the complete C code, analyze everything in the C code, manually fix the C code and do it, that itself takes even much a lot more time. And obviously, since mill and sill is not there at this stage, the quality of the software goes for a toss. But in model based development, since we are doing mill and sim, and all of these are done much quicker than manually developing the code itself, it basically helps us to produce quality software at much reduced cost. Okay, the number of headcounts is reduced here massively again. Okay, and apart from that, if you are using any sort of models for the given systems, from one OEM to another OEM, you can reuse these models efficiently and effectively. Okay, so that can also be done. So the last stage of it is like again, the reusability part and all is like very simple and easy with this. Okay, so this is about the different advantages of it. So what we call here as the requirement analysis. So the requirement analysis is like this requirement document will be there. He needs to understand this requirement document and he needs to try to convert it as a model. Okay, for example, here in this, so this is basically a switch algorithm. Okay, that is there. So this switch algorithm, when you try to replicate as a MATLAB model, it will look something similar to this what I have shown in the right side of the picture. Okay, so our job, whether we have developed this correctly and all, will only be known when you are going to validate. But to ensure that that we have actually completed this requirement means like we can tag the requirements in the Simulink model. So that process is what we call as requirement tagging and traceability. Just to ensure that I have developed this requirement, we tag the models, and there is a specific one called as requirement tag editor. So when you open MATLAB Beans, like there is in subsystems, there is something called as this requirement traceability. So under requirements traceability, you can link it to the requirement document. Say this is just an illustration that I have given here. So your requirement document obviously won't be very simple and easy like this. It will be very detailed document. So for each subsystem, we'll have like each like a para or a specific requirement number. So those requirement number and the requirement name, they have to be matched here. And based on that, we will try to create a traceability report, at least to ensure that I have not missed any requirement and I have developed all the requirements. To maintain that level of consistency, they follow these requirement tagging and all. And also sometimes, companies, OEMs and all, they will just simply buy the ECUs rather than taking the ECUs and doing all the, getting the ECU along with the flashed code. They just buy the ECUs and they keep it. They have their own development centers, like companies like Renault, Nissan, and Ford and all. For some of the specific projects, their own engineers will do the design development and all. So they just buy the ECUs and keep, and they do. So in that case, when they are going to go for some suppliers to just do the model development part. So these suppliers will do the model development part. They won't do the flashing part. They will just transfer the models to them. So in that case, we're doing these requirement tagging and all, it will be helpful for them when the companies get back the original model and they try to do code generation and when they try to validate it. So that's the first part of it, which is requirement tagging and traceability. So the next one is like the configuration settings that needs to be followed in the model. So again, I have told that there are certain standards and guidelines that needs to be adopted for model development and the model validation and all. So those standards and all, where I can go and find it means like in MATLAB under simulation and model configuration parameters, there is this gear kind of an icon that you can spot in the MATLAB tool. So when you just click on this, you can go there. It will have a lot of different parameters to control, like my solver, type conversion, model referencing, code generation target, simulation target, etc., etc. So here you can go, we can choose the appropriate settings and we can do a code generation. Okay, so that's the whole thing here. Again, it's not something like the engineers, the common fear that engineers would have is like, do I have to mug up and keep all of this? No, it's not like that. Companies usually provide documents. So based on the documents, you can stick to this and you can develop them. Okay, so that's the whole thing about it. So these are some of the common settings that they have with respect to that. I've just taken one example over here, how you need to define them and all that. So this is for simulation target and code generation. So under simulation target, we'll choose the which target platform the code needs to be generated, whether it's an embedded coder or an AutoSAR coder, or there is something called as target link coder as well. Okay, so that specific target where and how the code needs to be generated, all that will be fixed over here, and it will be chosen over here. Basically, you'll have a document where they'll tell that detect wrap on overflow must be on. So which means that I have to go here, I have to just enable this parameter in my configuration parameters tool. Something like that we have to do. Auto generate command, it needs to be on, means you need to select it on. Say, for example, an engineer is there. This person is new to the job. He's trying to do some of the changes. He does some of the changes while he has missed some of the changes. So where he can find it out means, we were talking about this model advisor report, right? So after finishing this, he has to run the model advisor report. Model advisor report along with my C code is a final deliverable file. So in the model advisor report, it will say that you have not enabled this specific setting. This is corresponding to this specific industrial standard. This is corresponding to this ISO standards. As per this ISO standard, this property has to be true, etc. Something like that, and all will be there. So all that he needs to take care of. So it's not like if I miss something, because a configuration parameters, there are like 200 configuration parameters for a Matlab model, 250 at least, I believe. So you need, it's difficult or impossible for someone to remember all of these parameters. But again, if in case this person is missing out on anything, means whatever that he remembers, he can make those corrections appropriately. Even in case he remembers, he misses out something, means he can run the model advisor report. From the model advisor report, he can fix it. Now the OEMs are coming up with different automation solutions where as and when my model is missing out on these parameters, see, they have created their own templates. So where I go and I try to start a development, means I need not open a Matlab model from scratch and try to change these parameters one by one. They will have a set template model, and I can just open the template model and I can start simulating. So the time that we spend on all of this is greatly reduced. So these are some of the things that the OEMs also work at the background. Apart from the actual development time and others, these kind of automations and others that they do also as something like a productivity improvement and things like that. Okay. So the next one is the model data dictionary. So again, with the requirement document, when we are trying to deal with different signals, means each signal is unique in its property. Okay, basically what type of a signal it is, what is the data type, what is the dimension of the signal, what is the range at which it is going to operate, and all that matters. So usually, as per our understanding, most of us would know something like, I have an M script, I will run that M script that will load my values into my workspace, and then I can call those values into my model and I can do the simulation. So this is the common practice that is adopted. So when you are doing like this, it has some practical difficulties. Directly when you are assigning a signal like A is equal to 2, means the data type by default it will choose as double. But most of the models that you are developing will not accept a signal with data type double. Okay, it is impossible to do code generation for signals having data type in double. Okay. Many of the OEMs won't even allow their models to have a value in data type double or something like that. So how do we handle? Again, another problem is there are high number of chances of data overwrite. Okay, like A is equal to 2, I try to simulate. Easily that A is equal to 2 can be overwritten as A is equal to 3. Okay, because this problem of overwriting of data type is very common when you're trying to do with when these values are called from the workspace, from the Matlab workspace. So to overcome that and to also maintain this data consistency, they have gone for something called as a model data dictionary. So what essentially is my model data dictionary over here? A model data dictionary is nothing but a repository. Basically, I have, let's say, 10 signals, A, B, C, D, E, F, something like that. Each will have a specific value. So instead of giving A, B, C, D, E, F as 1, 2, 3, 4, 5, 6 values like that, in an M file and then trying to run it into this, I will create something called as a Simulink data dictionary. I will link that Simulink data dictionary to my model. I will go to Simulink Explorer. Inside the Simulink Explorer, my Simulink data dictionary will be open. Over there, depending on the type of signal, whether it is a normal signal or a calibration value or a lookup table kind of a value, okay, depending on what type of a signal it is, I will identify that signal and I will manually enter the value into it. And that has this option of me allowing to choose my data type. Okay, when you are trying to run it as a script, I mean, when you're trying to put it into a workspace and run, by default, it will take double. And also, when you're trying to explicitly specify, you have to sit and write a code where in that code, I have to create each of these signals as objects. And then I have to define them as a UN8 or UN16, where it is a very difficult job. But here, it is a much easier one where I will create it in my Simulink data dictionary by click of a button. I can define manually the values into it and I can save it and I can close it. Okay. Once I save it in my Simulink data dictionary and I close it, my Matlab and my Simulink model will not refer back to my workspace. It will directly try to take it. It will try to run from it. So this is one of the approaches what most of the OEMs are following. So initially it was all mscript and loading the values, taking it from the workspace and running. Now, no longer companies, OEMs are following it. They have adopted this Simulink data dictionary. It is something like a repository that they have, which is easy to reuse and it reduces the development time and cost. Again, usually the OEMs come up with the list of variables and calibration data as in the form of an Excel sheet. So most of these companies again have developed automation tools where you just click a button, it will take that Excel sheet as an input, it will create the SLDD as an output, and that SLDD will be directly linked to the model. It's a matter of 5 minutes work. When you are trying to write a script for it, it will take 2 days. When you're trying to create a Simulink data dictionary, it will take 6 hours. That is 2 days means 16 hours. This will take 6 hours. But one time you create a tool, it will do the job for you in 5 minutes, 5 to 10 minutes maximum. So this sort of things and all have come with the data dictionary and data dictionary management. So this part of data dictionary management and data management and all, most of the people who are using Matlab Simulink are not highly aware of it. We all think that Matlab Simulink is for model simulation and others, but it does a lot more things. It does model into software into data management and all other things. So one part of it is creating a data dictionary in Matlab. So this is how SLDD looks like. So these are some of the set of values that I have. So these are some of the different signals that I have, which I have used for one of my project works. So these are some of the set of input signals. Their data type is explicitly mentioned here: minimum value, maximum value, dimension, storage class. So depending on the storage class, only my code will be generated and all that. So all of this is taken care over here. If it's an input signal, it will have a specific storage class. If it's an output signal, it will have a separate storage class and all the other things. Okay, so how are we editing the things? So I create a signal. After I create, see, I go here, I will click on this button which is present at the top. That stands for a signal. So once I create a signal, I double click on it, I can change the name. Then if I click on it on the right side, I will have a window where I can change the data type by pressing this. Dimension I can manually adjust. Minimum value, maximum value, storage class, everything I can change. So storage class is specifically used for the code generation purpose. If I am having a signal if it's an imported signal, imported signal as in a signal from a sensor. Okay, so if it is a signal that is coming from a sensor, you will have a different storage class. And if it is a signal that is going to a different subsystem, or a signal that is going to an actuator, an output kind of a thing, basically, you will be using a different storage class, which is basically an export kind of a storage class. So when you are defining an export kind of storage class, you have to explicitly define your header file and definition file. So based on the header file and definition file information that I have over here, I can, so based on this only my code will be generated. The final code, whatever my model is giving now, that will be generated appropriately based on that. Okay. And the next one is like managing the different signals. It's so one part of thing that we have done is like we have identified the signals and we have added them, whether they are input signal, output signal, or they are calibration value, or some signals can be like a local signal. Only within that model they will be used. They will not be used in any other model. Input signals, they are input into this model, but they can be coming as output from some other model. So they will be defined in some other model. So that signal, so like here I have like this is an input signal is volt. So volt will be an output for some other model. It is already defined there. So using import signal as, using the storage class as inherited means I'm inheriting the property of those signals. Okay, so that's it. So when I'm giving something like imported external, I will not define any of my data type. I'm sorry, I will not define my .c or .h file names over here. My tool will automatically take it. Matlab will automatically take it. When I'm trying to do a software integration, it will take care of all of these things. So that's not a problem over here. So the next one, when we go for output signals, means this signal is originating here. So I have a switch signal over here. When I try to give my storage class as exported over here, I have to also define what should be the name of my header file and definition file. Okay, so in that case, I'm giving my header file name and a definition file name. Appropriately, I have to give those signal names, and then we will be doing it. Okay, so that's one part of the work over here. Okay, so that's one part we have over here, and then that would be followed by the calibration signal names. So the calibration signal names are like your signal names is something like my sensor input and the actuator output. Apart from that, there are certain hard-coded values which you define into your system. You cannot erase it so easily. They are hard-coded into your system like that. So using some simulation tools, using some diagrams and drawings, we will identify that certain signals, your algorithms will have certain calibration data, and once you calibrate and give that data, you cannot reuse it. Those data are fixed basically. Okay, so for them, and so those signals list also you will be getting. So based on for those values, again you have to define, okay, what has to be my header file and definition file and all. So based on how we define it only, they will be coming in the code. So if you can see here, okay, for this given signal voltage, I have a uint 8 data type, minimum maximum value, unit, everything I have defined. So this is my code that is generated. So in this code, it will carry all the necessary information. Okay, how this code is generated, which version that I am using, which version of Matlab I am using, and how it is all there. All relevant information will be there. And this root volt means, like root means whether it is at the top level of the model or if it is inside any specific subsystem, all those informations it will give. And it will also tell that this is a uint 8 signal and volt. So when you are trying to type this line of code, see, again, your C code also has standards. Like how my Matlab model has different standards, my C code also has a specific standard that it needs to adhere to. Okay, so in this scenario, in this case, actually, to sit and type this is like next to impossible task. So you need to take care of that part here appropriately. All right. So all of this, the tool will take in when you're doing an auto code generation. The same stands for how your output signals, like how it is all declared and defined, and also for my calibration parameters in that specific header file and C file, it will all be there, and they are defined there appropriately. So apart from these things, certain things we need to at port property level. So all these port property checks, displaying the signal names appropriately, signal properties and signal control, signal resolving, propagating the signal, and all of these things, all of these comes under the SMART guidelines. SMART guidelines is actually a very big topic. Okay, MARB stands for MathWorks Automotive Advisory Board. Okay, so they have some set of guidelines. Based on that only, I have your model needs to be developed. Right from displaying of the signal name over here, okay, to resolving the signal or any specific signal properties, everything is controlled by the MARB over here. Okay, so once you resolve the signal over here means you have to define that signal in Simulink data dictionary. If you are not resolving that signal means instead of taking the signal name, it will take a junk name and generate the code. Usually the junk name would be something like input port number. It will generate code. For example, here, if you can see here, the volt is there. This I have already resolved in my model. Resolved as in, I have declared it in my Simulink data dictionary, and I will right click on the signal. I will go to the signal property and I will choose this option called as signal resolve. So once I do all of this, when my code is generated, it will give the correct name, extern uint 8 volt. Otherwise, what it will do is it won't take this volt. Signal name is volt. You might have declared it in Simulink data dictionary, but if you are not resolving that particular signal name, it will take the port number and it will generate a junk name. So that is not the right way of doing things. So when someone is trying to analyze the code manually, when someone is trying to read the code or analyze the code, it wouldn't have taken the signal names correctly. So there's an inconsistency that would be developed with the generated code and others. So to basically take care of these things only, we go for these port property checks and displaying the signal names and the signal. So this is what I was talking about. Signal name must resolve to Simulink signal object, right? So I have to select that signal and I have to enable this property, basically. So when this is for all the input signals at the top level in the model. When they are going to other sublayers, I have to propagate my signals appropriately. So this is what I was telling about. Yeah. So when the signal goes inside to multiple subsystems, it will be propagated like this within my angular brackets. So all this are some of the modeling guidelines that you need to follow. Okay. See, even without this, my code will be generated. But as far as the code quality is concerned, that will be very poor. Okay, so because you can generate the code, you can have the model, mill testing will give you good results, SIL testing will give you a good result. But when you try to convert this specific control model, when you try to flash it into an ECU means there will be inconsistency because you might not have resolved your input signal, but someone else would have resolved it at his end. For him, that will be an output signal. So he will have the name volt, which is resolved. It will try to search for the match. That code and this code will try to search for the match. Over there, that is an output. Over here, it is an input. It will try to search for a match. If the match is not there, ultimately, your package of C code will not be converted into a machine understandable language. It will cause a lot of problems. And where you capture it and all that is like how to check for consistency in my model. To check for the consistency in my generated code also, we will go to check for the quality of the code and others, we will go and we will run this model advisor report. So there I will go and run this model advisor report is in the MATLAB window, there is something called as analysis. I'll go to analysis, model advisor, and I will click on this. It will give me a pop-up. Just select the top level layer of the model. Click on this model advisor exam. Then if you can go it will list out something called as by product, by Simulink and others. We can click on by Simulink, and then we can try to run this. Okay, so when we run this, it will say that these errors are found in my model. So for example, I have just taken this screenshot over here. So one of them is like it asks to check whether there are any unconnected lines in the model. So unconnected lines means between one block and another block, there should be some kind of sort of connection. There shouldn't be any connection mismatches or anything. So here I have not connected this gain block and this output block. So it rightly says that there is the following set of lines are not properly connected in the model. Okay, so it is throwing as a warning over here. Okay, so the job of an engineer or a developer here is to ensure that your model does not have any error, or your model does not have any warning, or very minimal number of warnings and almost zero error. That should be the whole thing behind it. If there are any kind of warnings or errors which you cannot eliminate, you need to take prior consent from your design team or from the OEM that, okay, you have to tell to them that there is a model advisor warning that is coming. Is it allowed or not? Or you need to take consent from MathWorks whether it is allowed or not. So these kind of things and all an engineer has to take care and he has to work on. Okay, so this is with respect to the model advisor. So this will be finally followed by something called as code generation. So the whole thing of my control model, from the design stage, from the requirement analysis to converting the requirement as a Simulink model, then there are certain standards and guidelines my Simulink model needs to take care of to do even code generation or simulation, right from its internal background settings. And apart from that, your block level settings, declaring the signals, handling the different data type and others, all of this we have seen. So the final stage behind it is the code generation part. So in the code generation part, in the model advisor, we have defined the data type, dimension, and all other things. So once, like, since all of these were defined, we will go ahead to do the code generation at this stage. Okay, even in my SLDD file, that is like data dictionary, we have defined this part of it. What is that? Whether it's my input signal or an output signal, or it's a calibration, in which what should be the corresponding header file name and all. So all of this we will define, and based on that my code will be generated. So we will have something called as private.h, types.h, .c.h. A lot of these files are there. So based on this only my code generation will come. So this code generation report again will talk about the traceability. We were talking about the tagging and traceability, so that thing comes over here. Then about the different subsystems. So then static code metrics and all other things. Say for example, you click on one report, one file over here, you click on a corresponding signal, it will develop tags for you. When you're trying to view this via this HTML window, it will try to create tags for you, where you click on that, it will take you to the appropriate level, in what level it is there in your MATLAB model, in what position that particular signal is coming, in what subsystem the signal is coming. So basically, for a developer, as soon as he has generated the code, just to visually understand and interpret things and all, this will be very useful. This code generation report will be very useful for him. Okay, so and the next one is about the code generation settings and target. So about the code generation target, importantly, so there are different targets that your system takes. So with respect to embedded coder, it is ERT. Then with respect to, there is something called as AutoSAR coder, it is AutoSAR. Then with respect to other GRT, there is something which is generic real-time coder. So depends. This all depends on requirement. So what your OEM is coming up with and how you have to select it. Okay, so that's it with respect to the development part. So the next major thing that is over here is the testing and validation part. I think about the testing and validation part, we have already discussed about that at the start itself. Why testing is important, especially in automotive domain, and what are the different things as far as testing is concerned you need to take care of. So one thing that we saw is about the business criticality standpoint. Okay, because you have rolled out the car, this car is already out in the market, to come back to check for it and to fix it and then to go out. So this consumes a lot of time. The brand name goes for a toss, reputation goes for a toss, and all the other things. So that is one thing that we have seen. Apart from that, even from safety standpoint, it is very important. Say, for example, you have developed an airbag application, a crash sensor analysis application you have developed. You are now validating the software and you have released in the market. What if my crash sensor is failing? What if a crash is happening and my airbag is not deploying? So that can result in loss of life or serious injuries. Okay, so to prevent, as soon as your crash applies, within 0.01 seconds, your airbag must deploy. Okay, so that fast, that communication needs to be there. So how are we going to take care of all these things? So this is why the verification and validation stage is like very important for us. So as far as verification and validation is concerned, automotive companies, usually the OEMs or the suppliers, they will look for dynamic verification and validation, where they have to do both structural validation and then the functional validation. Structural validation and functional validation means, like say for example, my algorithm is addition of two numbers. Whether input A plus B is giving me C. Whether if I am able to do that, that is structural, that is functional validation. So as far as what is structural validation, now the twist is, we won't give simply as A plus B is equal to C. My A is uint 8, B is uint 16. If my C is uint 8 means, it will not give me the desired result, because A's range of values are 0 to 255, B's range of values are 0 to 65535, 3 bytes and 4 bytes. So my C cannot hold the value inside that range. It will cause data inconsistency, even for a simple addition. So my C has to be with the value, with the data type and range of B. So to identify these kind of things, we need to go for a structural validation. So both the functional validation and structural validation will be done at the model level or at the software level. And this is like completely spread across both model in loop and software in loop. Be it mill validation or SIL, SIL validation, we will take care of these. Sometimes, if necessary, we will do this dynamic level. So dynamic validation, it's not only functional validation, it is also a structural validation, where we have to identify about the different data type, dimension, min value, max value, and based on that only we will write our test vectors and we will try to validate the system. So this is what happens with dynamic verification and validation. So this is the complete thing that we were talking. So I have my functional requirement. That functional requirement goes into my plant model. So based on the functional requirement, I will write the test cases. Like the top level subsystem of my plant model, that will be converted into a model in loop testing template. Based, this test cases are there, So test cases are basically for different inputs, what are going to be my set of values and what will be the corresponding output. So when you are doing A plus B is equal to C for something like a uint 8 kind of a system means, so if it is uint 8 means, for example purpose I'm telling, if it's uint 8 for both A, B and C, means how I have to write my test cases. For the minimum value, I can give 1 plus 1 should be giving me 2. Perfectly fine. Then one value in between range, 100 plus 100 should give you 200. It works perfectly fine. And then when my uint A, B, C all are uint 8, uint 8 and uint 8 means, when I am going to give 250 and 250, output should not be 500. It should also be 250. The reason is my C is also uint 8. The maximum range of C is 256, 0 to 255. So if I'm giving me 250, 250 means my final output will be 255. If my model is able to give me exactly same behavior means, then I am testing it perfectly fine. So this is what exactly your testing must do. So whatever test cases that we have written, we have also covered the functionality part, which is dealing with addition of two numbers, and also the structural part, whether the signals are taken care. Now, since an error is observed here, he needs to go back. He needs to tell his OEM that the value of C is you, when both inputs are uint8, you cannot have uint8 as output. Better you can have uint16 as output, or a single data type as output, where the data operational range is more. So in that case, when they give 255 plus 255, will give 510 as output. So this is how your test cases are written. Those test cases are given to a model, your test. So this whole thing is called as a test automation framework. That is combination of my test cases, my test vector model, which will have my plant model subsystem taken input directly. Then my final test report will be evaluated. Okay. So after this completely happens at the model in loop testing stage. Okay, so tools apart from Matlab, even third-party tools like BTC and Reactus do model in loop testing. So the next part is software in loop testing, where I will do a code generation. So the generated final C code is there, that will try to develop a wrapper for me. So tools like Matlab or BTC, they also do this software in loop validation. So under that software in loop validation, we will be having a wrapper model that is developed. So this wrapper model, like whatever that is developed, I will replace my subsystem with this wrapper model. So this will look like a subsystem only, but inside that it will be a C code running at the background. Okay, so this wrapper model is nothing but an S function subsystem in my Matlab Simulink. So this again, for the same set of inputs, for the same set of test vector, I need to get exactly same expected output. If that is observed, then it is called as software in loop testing. Okay, so then it will be followed by hardware in loop, where my C code, whatever I have, see, one engineer will develop one specific algorithm. Like hundreds of engineers will sit and develop 100 specific algorithms. So all of them can be converted as a code, and then they have to be flashed into my ECU. So this whole flow and the whole part is there, right? So this is called as hardware in loop testing and validation. All right. So this is the different stages of testing that we have. Again, requirement analysis means it is acceptance testing. Specification analysis is system testing. Model integration is integration testing. Model development is unit testing. So I have my specific algorithm that I am testing at U level. Then, like my specific algorithm, tens and hundreds of algorithms which needs to be integrated together. So once I integrate all of them, I will merge all my test cases and test the integration testing. And final, and then apart from that, my specification is getting ready. I need to verify and validate whether all my specifications are developed using requirement tagging and other tools. So that is called as system testing and acceptance testing over here. So this is about the different types of testing that we have told. So, and apart from that, there is something called as coverage metrics that they have. Okay, whether condition coverage, decision coverage, and MCDC coverage. So whether, see, I will be using some specific types of blocks, right? Whether all the specific types of blocks that I'm using, they will satisfy conditions. If I'm using addition block, it's cases for the when I'm using a switch block, when I'm trying to compare versus an OR block or an AND block, it will all be different and appropriate. So, so to handle different test requirements and others, we will be using different types of metrics. So if I have to do any sort of decision-based testing means, I will go for decision coverage. When there are specific conditions that needs to be executed and validated in my model, we go for condition coverage testing. And the last one is MCDC coverage, where different combinations and state flow charts are used in the model. In order to validate them, we will choose it. So, like how we choose our code generation option, like ERP or AutoSAR, we choose, right? Like that, in my configuration parameters, under coverage, I have to go and choose my, among the three types, I have to go and choose one, and I have to do my testing and validation over here. So under this, if I'm choosing something like a decision coverage or a condition coverage or an MCDC, and if I am validating means, if in case certain conditions are not covered, if in case certain decisions are not met in my model, it will generate a final report and it will say that this particular part is not covered. You can retest it or you can add more test cases to substantiate your final result. Because usually in testing, what you have to do is, again, I will go back to that example of A plus B is equal to C. Ideally, if you ask me to test an addition block, I will only test for A plus B is equal to C. 1 plus 1 is equal to 2. That itself, if you're only going to do this testing means decision coverage or condition coverage, for that, it is fine. When you're going for MCDC means, apart from the yes condition, I also need to test for the no condition. Apart from U8 plus U8 equal to U8 for one of the yes condition, U8 plus U8 equal to not equal to U8 for the no condition. Even for that, I have to test and I have to give my report. So when I'm doing that kind of a testing, when I have chosen MCDC, I have to even write my test case in such a way that not only for the OK condition, even for the non-OK condition, as a tester, I have to write my test cases. So, so these are some of the things that need to take care of and need to work on. So this is how the final test report analysis comes. So whatever that is not covered or not tested, that will be highlighted in red. Like in this example, whatever I have shown here, this is for condition coverage testing. It analyzes different conditions. There are two input ports, input port 1 and input port 2 for a specific subsystem. So once that is highlighted in blue over here, no, at the top over here in the first picture. So this is the corresponding subsystem. So under that, it will check, it is checking for two input ports. In that, only one input port all conditions is satisfying. The second port is not satisfying the different conditions. So it checks for that, it analyzes for that. And based on that, it will give the report where I can quickly check this or analyze this. I can go back, I can fix it, and then I can retest my model. So this is with respect to different coverage and other things. So the last part of presentation that we have over here is advanced driver assistance system. So whatever MBD that we saw over here is, this is basically a crux or a base that we have for our system. Okay, so so MBD is something that can be applied for any kind. You take a powertrain control module problem, you take a battery control module problem, or you take any other different system. It can all be worked around and analyzed based on this. But one specific system, if I have to talk, means I'll probably take an ADAS application. The reason why I'm showing an ADAS application over here is like, ADAS is something like I have personally, I've been working on this problem. And ADAS again involves a lot of different varieties of sensors and all, where they are trying to achieve complete automation, a complete autonomous vehicle. So when we are going for something like a complete autonomous vehicle, the algorithms that we need to develop should be foolproof. The models that we are trying to develop there must be foolproof, and all the other things. So this is with respect to the advanced driver system. So some of the different problems that is there with advanced driver assistance system is like adaptive cruise control, autonomous emergency braking, blind spot detection, front or rear collision warning, cross traffic alert, and lane changing alert. So these are some of the ADAS problems for which OEMs and Tier 1 suppliers are working on different solutions for. Okay. And as far as the level of autonomous driving is concerned, I think this is something most of us are familiar with. Our normal cars used to be with at level 0, where we must have complete hands-eyes coordination, where there will be zero assistance or feedback from the vehicle to support our driving. But as the level keeps going higher and higher, naturally we can take away one support after another. We need not have any kind of hand, or we need not have any eyes to look at the road. And the complete autonomous driving is the level 5, which OEMs are actually thriving to achieve. Not all the OEMs have achieved this. A few OEMs have actually achieved this. Tesla is at level 4 of testing, where a guy will be sitting at the driver's seat, but he need not control the vehicle. When he finds that my vehicle is trying to go out of control, he can quickly catch hold of the steering wheel and he can drive. Okay, so this is level 4. And up to level 2, it will be assistance. Assistance as in, it will be an open loop kind of a system where it will tell that, if I'm driving on the wrong side of the road, it will provide a warning to my steering wheel saying that you are driving on the wrong side of the road. But at level 3 or level 4, it will automatically prevent the driver from driving his car to that. Automatically, the brakes will be applied or the engine will be turned off when my vehicle is in the level 4. So these kind of things are basically associated with levels of autonomous driving. So the major ADAS stakeholders in today's automotive industry are companies like Bosch, Continental, Ford, Harman, Renault, Nissan, Tesla, BMW, Delphi. So these are some of the major stakeholders that are there for advanced driver assistance system. And any projects that you take, see, most of the Indian OEMs, say people like Ford or Renault, Nissan, or Bosch, so these companies have their development centers set up in Tamil Nadu in India. And for most of these companies, they have projects associated with advanced driver assistance system. So as far as, even put aside advanced driver assistance system, the major thing that companies are looking among engineers is like they want quality engineers who can get the job done with good. See, they are expecting people with good C code knowledge, not C programming. Good C code knowledge. They need to be able to understand and interpret a C code. That is one. The next thing that they are looking at is like they are looking at engineers with a good amount of Matlab simulation knowledge. You give a problem, they need to give a Matlab solution. So that kind of expertise that they are looking at. And apart from that, once you get into a job and you try to gain a lot of hands-on experience, you can equip yourself to MBD standards or model in loop or software in loop, handling different tools and all the other things that is coming. So these are some of the industry demands for a model-based development and design engineer. Basically, you need to have good simulation skills. You need to be able to review the requirement, develop models as per the MARC guidelines, create test cases and testing scenarios, perform model in loop, convert your model to a code, uh, either by AutoSAR or embedded coder platform, and do software in loop testing and validation. And almost all the OEMs and all the tier 1 suppliers, at least in our state or even in India, like even Mercedes-Benz or like Ford or Robert Bosch, you name it, those companies, for not only for ADAS related applications, for different applications, they actually have it. So this is basically about the model-based development and validation. So with this, I've come to the end of my presentation. So that's it about model-based development, especially from practical standpoint. That is right from knowing the pain area to it and trying to do a code generation and trying to validate it at what levels it is there and all. So this is about the model-based development things.
Hello, Balaji.
Yes, ma'am.
There are few questions in chat box.
Yes, ma'am. I'm opening it. I'll quickly start with the questions, ma'am. Yeah. I think there is not much questions I can find in the chat box. So if people are having any questions,
Somebody asked.
One question.
Yes, ma'am.
Being a beginner, if I have algorithm in Excel, can we directly convert it into machines language codes? If yes, how?
Uh,
And can I directly
it
test
is
that
always
algorithm?
okay. So one thing is, for a beginner, you cannot convert your algorithm into a machine language code. Your machine language code is not a C file, not a mere C file. Your machine language is something that will be in the form of zeros, ones, along with my object file and .a file. So there are certain tools and packages. Most of these tools and packages are OEM specific. Okay, Bosch has their own set of tools to convert C code into a machine language code. So ideally, for a beginner, you can try to convert your algorithm. Okay, algorithm in the form of an Excel is basically an Excel requirement document. So you can convert your requirement either to a model, validate it completely, convert it as a code, number one. Or the second thing that you can do is, you can directly, if you are very good with your C coding skills, and also the C code is as per industrial standards. The problem with most of us is, like, the current industrial standards are so high. Okay, right, you have to even write from the specific set of comments that we are giving, no, even those things will be very specifically noted, and it will be looked upon. So in that scenario, we need to it's always advisable to develop a model, industry specific model, check whether my model is as per industry standards, convert it into a code, and then we can share it. I mean, we can then convert it as a machine understandable form, and then we can directly test it in the hardware. That's the thing. So, okay, one more question that I see is, what is the effectiveness and efficiency of ADAS in high density traffic and mixed type of vehicle? Okay, so one of the common problems that most of the OEMs are facing is, like, driving in high traffic. Uh, like how most of us are familiar with adaptive cruise control. So adaptive cruise control is, I sit on my vehicle, to explain to a layman, adaptive cruise control means I sit inside a vehicle, I will set my vehicle to drive at a set particular speed, like 50 kilometers per hour or 80 kilometers per hour. My vehicle will keep running at that particular speed, and when there is any object that is coming in between to my vehicle, the driver has to take control, and he needs to control the vehicle. So it is partially autonomous. So adaptive cruise control feature in one way is a partially autonomous thing. Okay, so this is for a highway driving we have adopted. Likewise, there are different algorithms that is related to lane changing, or slow driving kind of a features, or where I sit inside a vehicle, my vehicle will be fitted with different radar sensors and others. And depending on the range of my radar sensor, whether it is in close proximity or farther proximity, my vehicle will move at a very specific slow speed. Okay, so this is basically with respect to high traffic density related applications. So yes, okay, as far as my knowledge is concerned, different OEMs have projects in which they are, like, working towards it. And specifically, again, while validation, see, they no algorithm is developed for type of vehicle. I am driving a specific car, it will only treat an object in front of me. That object in front of me can be a human, that object in front of me can be a bus, object in front of me can be a cycle. Okay, but while he is trying to validate that algorithm, okay, while doing some sort of a software in loop or a model in loop testing, depending on the radar feedback that he is getting, he can try to effectively test it across different set of vehicles. So I think that has answered your question here. Okay. So are results of Typhoon Hill always acceptable by industrial experts? What are the other professional hill softwares used in the industry? Sir, on the first part, I do not have any sort of an idea on what Typhoon HIL is in first place. But again, there is no restriction in industry that only a specific hill software needs to be used and developed. Okay, so in my current understanding and knowledge, it's all depending on the OEM. Okay, so if he wants to develop and if he wants to do HIL validation with ETAS, or if he wants to do a HIL validation with DSpace, he can go and he can work along with that specific OEM, and they can do HIL validation. Basically, there is no stopping or anything like only specific things needs to be done, but certain OEMs will have certain preference. Like, say for example, if you are doing any smart camera related testing and validation, they will generally adopt for National Instruments and their products, because National Instruments are pioneer with respect to smart cameras and others. Okay, but when you are trying to look at any powertrain related components HIL validation, obviously they will seek the expertise of DSpace, because they are pioneers with respect to that. Yeah. So the next question I can see is, can you please suggest the scope and opportunities in this field for our students, like internship and any kind of a training? Sir, yes, as far as the opportunities for students are concerned, there is a great level of opportunities for students as far as model-based development is concerned. So if you can ask me, like from my batch itself, there are a lot of my friends who have passed out of PSG College of Technology. Like, we have been working in different OEMs like Continental or Robert Bosch, a lot of my classmates actually, in Mercedes-Benz and other companies, where most of us are associated with projects similar to this. If one friend is working in body control modules, I am working in ADAS. So always, as far as the students are concerned, they should be good enough to learn the process and algorithms in first place. I mean, how to convert your algorithm into a code. So this process and simulation modeling skills is what they need to develop in first place. So that's the whole point, sir. And also, when you get a job into any top OEM, usually the companies will train you to those things. But apart from that, now there are some small companies that are there in the market who are training students specifically to do this. Okay, say for example, if someone is wanting to learn about model-based design means, there are some specific companies. They're not OEMs, but they have these lectures and courses, like how Coursera or Udemy is having different courses. So these guys are also having different paid courses where you can even learn and you can do it. So that's as far as like my knowledge on this is concerned. Can we simulate different driving behavior? Yes, we can simulate different driver behaviors, and we can feed those data into the system. Okay, so whatever I have showed you here is only one part. Whatever I have showed you here is validation of the final software product that is going. Okay, like this is one part of verification and validation. Likewise, when you are going for ADAS, another part of verification and validation, there we will be seeing about different driving styles, in which place you are driving and all that. So when you are doing, I mean, there are some customized ADAS related verification and validation tool. Whatever I have shown you in this presentation is only one part of the thing. In another part of it, when you're talking about some specific ADAS verification and validation tool, there are tools where the driver behavior, the driving map, everything will be recorded and will be fed into your computer, and based on my simulation software will be flashed into it. Like how my C code is put into a model and it is validated. Likewise, my plant model. So whatever we have seen is about the control model and the control algorithm. The other side of it is the plant model and the plant algorithm. So at that side, as far as plant models are concerned and the plant model behavior is concerned, there are some specific tools. For powertrain control, tools like GT Suite are used. For ADAS related applications, we have tools like a car maker and others, where we will be analyzing the different driver behavior, driver settings, different routes, and others. I mean, different drivability routes and others will be defined, and based on that, we will go ahead to test and validate them. So this is one. I mean, so that is also possible with this. So I think with that, I think most of the questions are covered, I guess. Any further questions?
Hello, Balaji.
Yes, ma'am.
I think you have covered the entire thing. For the past 5 years of experience, you have shared the entire thing. I hope participants have got really a wonderful experience, wonderful knowledge sharing session.
Yeah, ma'am, I can find a couple of questions. Can you suggest some books on MBD? I think MathWorks, you don't have any specific books for MBD, but as far as if you want to learn more about MBD and different processes that is there with MBD, you can start with model-based design or model-based development Matlab Simulink. Just Google this, and you will have a lot of training materials and videos that is there as a part of in MathWorks website, where you can learn on this. And as far as open source software is concerned, so whatever that I have shown, right, the model development and the validation and all, it can be done with Matlab Simulink. Again, Matlab Simulink is not an open source software, but that is also available in the market, where like you can download a cracked version of it and install. So maybe if people have access to Matlab Simulink, maybe you can get started off with this. As far as MBD, model in loop using Matlab Simulink, software in loop using Matlab Simulink, everything it can be done at the simulation level using simply Matlab Simulink too. Even tools like BTC or embedded tester are there, but these tools, like currently most of the OEMs, like actually they work and they support with it. So and they are not, again, third party. I mean, they're third party tools which is not like open source or anything. So probably I think with Matlab Simulink you can start off with. And there are certain guidelines documents as far as MAB guidelines I was telling, right? So MAAB, it is MathWorks Automotive Advisory Board, it is. So you can Google that. You can download the MAP guidelines document from the Google. It is readily available, probably third or fourth search link in the first page you will get it. So based on that, you can download, you can try to understand that. Again, you can switch back to MATLAB. So right from block by block, for different individual blocks, what are the settings, what are the other things we can you can probably check and you can work. Okay, so the last question I see here is like open source code or design available for BMS design of EV. So I have not worked on anything related to battery management system or EV. So sorry, I have my career has been with powertrain control and then followed by ADAS applications on MBD, and then about even I have worked on different levels of manual software development on hill model development and others. So sorry, like I don't have any answer for this question basically. Karthik Hari, like, yeah.
Can you share your mail ID?
Yes, I'll type in the chat box, so you can take my mail ID. With this name, I'm also available on LinkedIn, so you can probably, if anyone is interested to know more about this, you can probably send me a LinkedIn request, or you can put me a message on LinkedIn, where probably we can even interact offline a lot more on this. The same name, I'm available on LinkedIn. So I think that's it from my end, ma'am. So I have covered the
Okay.
points, and probably the presentation I'll be sharing it with the PSG Tech faculty, and so we can
Thank you very
get
much,
it.
Balaji. Thank you very much
Yeah,
for sharing your highly knowledgeable session they had. Thank you very much. Thank you.
yeah, thank you. Thanks, ma'am. Thanks for the opportunity as well. It was
One
nice coming
request,
back.
one request from my side. Can you
Sure.
give any training for our ME students so that they can get?
Yes, ma'am. It is possible. Maybe offline we can discuss on
Yeah.
this, and then we
Yes,
can
of course.
maybe even if it is something like a hands-on session. I
Yeah,
think.
that is what required for them. So please keep.
Yeah. Sure, ma'am. Sure, ma'am. We can discuss on that
Okay,
offline,
we
ma'am.
will
Definitely.
discuss. Okay. Thank you so much.
Yeah.
Participants,
Thank you, ma'am. Thank you so much, ma'am. Thank you. Thank you all. Bye.